Okay.
So the first model that we covered today is this machine replacement model, where machines are allowed to break down. Notice that in Thompson's model, machines deteriorate over time, but they don't fail. Chen and Schwartz, on the other hand, decides that the machine should fail over time, and that is one way to have a machine deterioration. But then they simplified the other aspect of the model. Something is going on. Okay, so then the other thing that they did is simplify the model in another direction, because generally speaking, what happens is when you generalize a model, sometimes you cannot generalize everything. You generalize one aspect, but then you have to simplify the other aspect in order for the model to be reasonably transparent and not too complicated. So the second thing, the simplification was that while the machine is working, it is giving you a constant rate of production. So the only deterioration that happens is that the machine is becoming more and more prone to failure as it becomes older. So that's so there's a deterioration, but the deterioration is of this different kind. Thompson's model, the production goes down as machine becomes older, and you have to maintain it to keep it up. In Chen Schwartz's model, the machine deteriorates by being more prone to failure. But while it's working, it's good. But its probability of failing is going increasing, and the maintenance then tries to decrease that. So this is another way of maintenance. The maintenance is affecting the breakdown probability of the machine. Okay, it's an interesting model, and we will see some other things that go with this model. And I personally like this model a lot. And not only that, I've done a lot of effort to provide an economic interpretation of some of the complicated equations that arise in this model. But I also, with Ben Susan, our other colleague, have completely redid this model in a proper stochastic control setting, which Chen and Schwartz neither knew nor aware of at that time. Stochastic control was still not very advanced at the time this paper was written. And on the other hand, Ben Susan is a world-renowned expert on stochastic control, with neither Chen and Schwartz and no others can claim to be. Okay. So T is the sale date of the machine to be determined. So they keep the focus also on the fact that the machine could be optimally replaced or sold, rather. You not replace. Remember, it is not really a replacement model. It is actually a machine that will be sold. So I think the maintenance and replacement may not be the right way to describe this model. The maintenance and a sale date for a machine subject to failure. Maybe I'll change that. Okay. UT is the preventive maintenance rate at time t. R is the constant positive rate of revenue produced by a machine functioning, but is independent of its age. Okay? And this is net of course, the cost of maintenance, which is we are trying to optimize. There's a discount rate, and there is a junk value of the machine, which is L. When the machine fails, you get L. Okay? So that's kind of the model as it contrasts from Thompson's model. Then BT is the resale value of the machine, and B dot T is less than or equal to 0. This is given. Okay? This is, you can get it like in a car. In the case of car, for example, there's a blue book value of how old the car is. So you buy a car, and then you can see some of the cars how the blue book value of this car goes down as time goes down, as time increases. So BT, which is the resale value of a functioning machine, you are not going to sell a car if it's already broken down, but you may have to junk it, and that's a junk value L, which can actually be negative in some cases. But Chen and Schwartz uses it a positive junk value. And so we have a given function that gives you the value of the machine as time progresses. HT is called the natural failure rate. It's also called the hazard rate in reliability theory. It, generally speaking, bigger than or equal to 0 because it is a failure rate, and it actually increases over time. So a machine is prone to increasing failure rate over time. Now here comes some of the interesting aspect of the model. The hazard rate is defined in terms of the probability Ft, which is a cumulative probability that the machine has failed by time t. Okay, so that is called Ft. There's also a cost CUH. Maybe I should put CUH before Ft, so it is more transitioning to the next slide. The cost of machine depending on the preventive maintenance U when the natural failure rate is H. Okay, so this is their way of defining the cost of maintenance. To make economic sense, it's reasonable to assume that L is bigger than 0, although that may be less than 0 sometimes, but this is what Chen and Schwartz does. I think it's not unreasonable. The scrap value of the machine, it might have some steel and it might have whatever, some parts that can be salvaged. BT certainly should be bigger than L because BT is a functioning value of the machine. And BT should be less than the economic value of the machine, which is given by the present value of the revenue generated by the machine without any preventive maintenance and without assuming that the machine will ever fail. So if the machine were to produce at the rate of R a revenue all the way to infinity, and you capitalize that revenue rate by a discount rate rho, then that present value is given by R divided by rho. Surely BT cannot be bigger than R divided by rho. Okay? And so that is reasonable. And then we have a UT, which is just for simplification. You can put any value, any upper value to you want, as long as you don't allow infinity, because that may bring you to some other issues. And so we have a control upper bound. The natural rate, okay, the CUH in Chen and Schwartz model is assumed linear. So it denotes the cost of preventive maintenance U when the natural failure rate is H. So it is assumed to be the following. It's not, no, I take it back. The CU is not linear, it is linear in H. But so what's going on in here is the following. What Chen and Schwartz assume that there's a natural failure rate H, and if I maintain the machine at U, preventive maintenance at rate U, then I reduce the natural failure rate to H times 1 minus U. Notice U is between 0 and 1, so I can put 1 here. If it was M, then I may put M. But that's only add one more variable to it. It doesn't really create any issues. So this is a natural failure rate, and this is a controlled failure rate. And what Chen and Schwartz is saying is that if I want to decrease the natural failure rate to the control failure rate of this amount, then I must pay this amount of money, CU times H. So it does depend on H, okay? And it depends on U in a nonlinear way. We assume that cost of no maintenance is 0. We assume that any maintenance is positive, cost positive, and we assume that more and more maintenance will cost more and more money, okay? So it basically means that if I want to have an absolute reduction from H to H1 minus U, then that reduction becomes more and more costly as machine becomes older. Because remember, we're describing this whole function now, a function of CU and kind of H. And so that's kind of the whole idea here. Okay, so once we have this assumption, we go to the control problem formulation. And this is the definition of hazard rate in reliability theory. It's defined by the rate of the failure or the conditional probability of the failure given that machine is still working. Okay, because F is the cumulative probability that the machine has failed by time t. 1 minus F is the cumulative probability that the machine has not failed by time t. And so this says the conditional probability of machine breaking down in the next delta amount of time, and then delta goes to 0. So this is kind of a rate given that machine hasn't failed yet. So that's a conditional probability. And that conditional probability, which is given here, is called hazard rate, H of t. Okay? H of t is increasing as the hazard rate is increasing. And that's reliability theory. What Chen and Schwartz does is tweaks the reliability theory by saying that if I maintain the machine, then the control hazard rate is this amount. And that would govern this dynamics, which is reasonable. And if you put 1 minus F on this side, you can see that this is like a state equation. So I have a state equation of an optimal control problem, assuming that at time 0, the machine is still working. Okay, so F0 equal to 0. And the control failure rate is this. Notice this is our X state variable. There's one difference, however, which is very important when you ever go back to or go to read Ben-Susan-Sethi paper in management science, which is Chen and Schwartz model, but done in a totally different way. And I would say much more properly than Chen and Schwartz. The reason why Ben-Susan and Sethi write a stochastic control problem is the following. F is not observed. You cannot observe a probability. You can given a particular function over time of maintenance rate, I can put that maintenance rate and I can calculate that mathematically, but I cannot observe it. Remember, in stochastic control, the control should have a feedback on the state. And the feedback on the state means that if a control U is a function of F, then I should be observed. I should be able to observe F at any given time. Otherwise, how I'm going to implement the control? But F is not observable. That's why we had to start a proper model. But it came a lot later. It is like maybe 10 years ago or so I wrote that paper. Okay, let's continue. So in order to define a control problem, I got the dynamics. Remember, the control theory doesn't care. It is a state equation, proper state equation for control theory. It doesn't know whether f is observed or not observed. It is a mathematical problem, and it is perfectly fine. The question then is, what is the objective function? And Chen and Schwartz, I believe, is quite clever in coming up with an objective function, which is as follows. It says, I want to maximize the expected present value of the machine, and it is three different terms. First is the revenue less the cost of maintenance, which is R minus CU times H. But notice that this maintenance applies only while the machine is still working. So if I take the expected value of that, I should multiply with the probability that the machine is still working. So this is your revenue minus the cost of maintenance times the probability that machine is still working. The second term is that at some time t, the machine may break. And when the machine breaks, I get value L. In order for me to take the expected value of this, I have to multiply with f dot and integrate from 0 to t. Because machine is failing with some probability at each time t. I observe it only when it fails. But there's a probability that the machine is failing at each time t. And whenever it fails at time small t, I derive the value L. So since the probability of failing the machine is kind of infinitesimal, if you think about it, it's f dot times delta, and delta going to 0. And I take the L value when at that time t. That's a rate, so I have to integrate that. So that is the integration. If you take the integration, that is the junk value of the machine when machine fails. Machine fails before it is sold. Okay. The third one, so this is, we have to integrate those. So we integrated that because this is coming as a rate over time. This is coming at a rate over time. This one is coming as a lump sum. So at the time capital T, I sell the machine. I acquire B of T. I discount it. So the present value of that is e to the minus rho T times BT. But I only can sell if the machine is still working. So I have to multiply that with the probability the machine is still working. Chen and Schwartz claim that this is the proper objective function for this problem. If you believe this to be a proper objective function, then I can substitute f dot from here. And when I substitute, I get this. Notice now, this is exactly like a special case of control problem that Kushali, I send you a slide where this term, this 1 sub dt term has to go with this guy, with this bracket here, okay? Do you hear me? Okay, so that j has to be moved here and this term goes up here. So it is easier to follow. Okay. So notice now, this objective function is integral from 0 to t. We have a control. We have a state. We don't have f dot anymore. We have a state, f, and we have a salvage value in terms of the state at time t. Okay, not observable. Of course, it will be observed when it breaks down, and it will be observed when it is not still working. But those are the only things you can observe: breakdown and it's working. Those are the binary things that can observe. That's the basis of the model of Ben-Susan-Sethi. Okay, so now I have a control problem and I can apply maximum principle. That's what Chen and Schwartz did. And if they properly found a proper objective function, then their model should give you the right solution. And it does. But what is a proper objective function and how you take expected value is basically an intuitive kind of thing here. And if you did something else, then the solution would not be proper. And what Ben-Susan and Sethi find out, forming the problem exactly, that we get the same solution. But let me say a little bit more. We get the same solution, and when I send the paper to Chen and Schwartz, Chen replied, because I knew Chen, he replied that at least I'm glad to know that my published paper in management science is correct. And yes, it is correct, but only in some way, in the sense that even though I find the preventive maintenance UT all the way from 0 to capital T. Notice now, I'm finding this from all the way from 0 to T. But if the machine fails before T, I only implement the preventive maintenance up to that time when the machine fails. Even though I found the optimal maintenance after that time T, I don't apply it. Even though I have optimal maintenance rate after that time T, but I cannot use it anymore because the machine is broken down. And because machine is broken down, you can sort of see that that captures in some way that I'm only capturing that maintenance cost only while the machine is working. But I also compute the maintenance rate all the way to capital T, which can be infinity. I mean, not infinity, but it can be a long time. And so I'm basically, whereas if you take the stochastic control model, you will have a feedback on the state of the machine, which is either working or not working, and you will only have a control defined for machine when it's working, and when it's not working, the control would be 0. Okay, so that would be a similar way of saying it. Chen and Schwartz cannot afford to make the 0 because it doesn't know. Because the problem being solved at time 0, it doesn't know when the machine is going to fail. So it must try to compute all of that. Okay, and it's okay. It seems it's okay. Since the finite horizon problem, it's okay to use standard Hamiltonian. It's also okay to use another one, but I prefer to use this one, and Chen and Schwartz use this one, so let's just keep it with that. So I have a Hamiltonian, I have lambda dot, and I have lambda t, which is just the derivative of this guy. Just a second. Okay. So we have adjoint variable, we have adjoint terminal condition, the transversality condition, and we can continue One more thing that we need to do is, since we also must find the optimal capital T, we have a condition 3.77, which gives you condition for terminal T to be optimal. And that condition is given like this. Now, this condition is rather complicated, and one need to provide an interpretation, or one would try to provide an interpretation of what all this means in economic terms. And notice that the explanation I'm giving you appears in the third edition, which is now. It appeared in the second edition, but not as good. It appeared in the first edition, but not even as good. So over time, I have improved the exposition of this condition. And as I was reading this again, I believe that I can improve it a little bit more, but that improvement is simply, I will mention to you what I mean by that. But that improvement is kind of parallel to what I have. Okay. So let us proceed to interpret exactly as we have in the book. By the way, did anybody read this? I mean, I assume that all of you read this. So suppose I'm now at T star. I found, well, the only time I could be at a T star is if the machine did not fail earlier. I found the T star using this condition. I am at T star because machine didn't fail. And I am trying to find out what is the meaning of this T star. Well, when I'm at T star, I can do two things. One is I can not sell the machine for another delta amount of time and see what happens. Clearly, I would like to discover that if I change the T star to T stars for delta, I will lose because T star is a maxima of this machine. So if I increase it by delta, I would lose. On the other hand, since I already knew T star, I solved the problem at time 0. If I stop and solve the machine T star minus delta a little bit earlier, I should also lose. What I'm giving you now is an explanation of loss when I not sell it at T star, but sell it a little bit later. Okay, that should be 9.9. This is still exercise 9.8. This is exercise 9.9 for delta less than 0. In that exercise, you're asking the same kind of explanation when delta is less than 0. Okay, so that is an exercise. Let's just do the first part. This is still fine because that one is asking you to derive this condition starting from 3.77. So there are two exercises related to this. One is to derive this condition by using 3.77, which is just a straightforward derivatives of Hamiltonian and the condition that we know at 3.77. So that is just the calculus exercise. The other exercise is doing what I'm doing for delta less than 0 and trying to find out all the meanings of the terms in that setting. And I think it would be nice. I did not have time to write a solution of this in the solution manual. But if somebody works this exercise 9.9 and provides this explanation, please feel free to send it to Kushali and we'll type it up and put that in the solution manual. Okay. When you take the derivative from 3.77 to arrive at this equation, you will find that there is a common term that will appear. This term multiplies this entire term. Because it multiplies entire term and the whole thing equal to 0, I can remove this term because it is strictly bigger than 0. Okay? because that's bigger than 0, and ft star is definitely not 1, because if it's 1, then I will know that the machine will fail exactly um, at T star, even if it didn't fail earlier. So that is not a good model, because it's a stochastic model, not deterministic model. So you you could explain this equal to 0 along with this. I could multiply this back here and then provide the explanation of everything. But Chen and Schwartz also removed this, so this is all the term we have. So I'm trying to explain this. Sometimes it's better to explain the whole thing, but it's just too many terms and too many long expressions to write. So I will try to explain that. In order to explain that, we need to know what is the consequence of this. So when I remove e to the minus rho t star, it means that these terms are now considered to be current value at t star. Because if I multiply this whole thing by e to the minus rho t star, then that's a present value. Remember, the problem was in the present value. We had a standard Hamiltonian. But interpreting the condition 9.34 in the present value term and the current value term is not that much different, because all it means is that this multiplier term e to the minus rho t star, which is a constant. So either meaning would be the same. Okay, so all I'm trying to say is now this term is to be in the current value terms at time t star, which is important to know, because we will see when we do these terms, we need to put everything back at capital T star and not at 0, because we already removed this term. So let me say the following. You are all PhD students who will be writing papers, and you will be coming up with such equations, which the referee will ask you to provide interpretation if you didn't already. And it turns out that sometimes it's not so easy. And you have to make a lot of special effort to put words into for an equation. Okay? And there's another thing I think I already talked to you about, is that until you explain this thing, it might look counterintuitive. But when you explain everything, it becomes transparent. So it's counterintuitive until it is intuitive. You understand? And our society pays a huge amount of dividend for you to provide this kind of explanation. So I am taking time slowly to tell you how I am proceeding to interpret this equation 9.34. And I also tell you a little bit more of how I could have done it, which some people might find more interesting, but it is equivalent. So this is the first part. But I also removed this term, 1 minus ft star. This also, well, this means that the entire terms have to be explained with this term. So what I'm trying to do is, we can say that the presence of this term means that the machine will be replaced at t star if it hasn't failed by time t star with that probability. Remember, if the machine failed, there's nothing to do. T star doesn't come into play if it fails before t star. But if it doesn't fail by t star, then the machine is working, and I can sell it. So in some sense, when I remove this term, I'm essentially saying the machine is working at T star, and I'm only interpreting a working machine. That is tantamount of putting F_T star equal to 0. Okay. So that means the machine is definitely working at time capital T star, and F_T star equal to 0. And then this becomes 1, and this is a condition that we want to interpret. So keep that in the mind. Back in your mind, keep that. Because if I put it back, some of these terms may acquire better meaning for you in some sense. Okay, so you just keep that in mind. So now we come to the next stage. We're now going to start skinning this cat in a way. Maybe there are 9 different ways to skin this cat, but this is one way. Consider keeping the machine to T star plus delta. Immediately, we lose BT star. Because if I don't sell it at T star, I don't get the money for selling the machine at T star. So my immediate loss is the loss of selling price BT star. Remember now, I have to find the consequence of everything that happens when I decide not to sell the machine at T star, instead sell it at T star plus delta. Okay, so I'm trying to find the consequence of all of my action when I postpone the selling the machine to T star plus delta. Okay, but we gain other things. Even though we lose BT star, we gain other things. Well, the first thing we gain is a revenue from T star to T star plus delta. Okay, so that I'm writing this way. Okay, so let's go one by one. It's a lot of explanation here. So I'm writing this. Okay, this revenue that's coming during this delta period of time, but it's a small amount of delta, so I can assume that to be constant, and I multiply that by delta. And I also have to discount it by e to the minus rho delta. But we will see that that is not so important because it is coming from T star to T star plus delta. You can discount it somewhere on average, but it's a small amount of time. So you will see that as long as you consider that, it will factor out automatically. Okay, so we will do that. The second thing is the following. If I keep the machine for T star to T star plus delta, I'm risking the machine to break down in this delta amount of time. Anywhere between T star to T star plus delta, the machine can break down. And I get this value when the machine breaks down. And so this is the term that I have. And the third term I have is that I will sell the machine at T star plus delta now, if it is still working. So that's the third term. I'm going further. Okay, so I'm just telling you, these are the gain terms. We will see why these are the gain terms a little bit more, but each of these terms makes sense. I get more revenue. I expose myself to machine breaking down, and I get selling price a little bit later. These are all the consequences that I have. Now, when you have this, I'm looking at the right-hand side. The right-hand side can be obtained by using expansion of e to the minus rho delta term and expansion of bt star plus delta by using Taylor series. Okay, so let's do that. E to the minus rho delta is 1 minus rho delta plus little o delta. Okay, so as delta goes to 0, this term goes to 0, this term goes to 0, and I'm stayed with 1. So you can see I'll just leave and it O delta. I leave with this and O delta. I haven't put delta going to 0. I just put that as delta plus O delta. Okay. I do the Taylor series on this one. It's BT star plus B sub T star, which is the derivative with respect to delta O delta. And I have F T star plus delta, which is F T star plus F dot T star delta. And I substitute for F dot T star this term. So I get this term. So what I'm now trying to say is that I am not letting delta go to 0 yet. But when I do this, I get all of these. Okay. And so these are the terms which are, so these are the terms 9.35, 9.36, and 9.37 are now trying to interpret what these are. So we got the gain, we now interpret what these are. The net gain is the sum of these three terms minus BT star, right? Because we already lost that. So the net gain is the sum of these three terms less BT star. Let's go one by one. 9.35 gives the net cash flow, revenue minus cost of preventive maintenance from T star to T star plus delta. So this is from T star to T star plus delta. From here times delta, because I have a delta amount of time and an O delta. 9.36 represents the junk value multiplied by the probability that the machine fails during the short times delta. When the machine is found to be working at T star. That means that it may fail between T star and T star plus delta, and I will collect that junk value, and that is the value that we get here. Last one is 9.37. Now 9.37 is given by this term. Since I have to substitute, I have to reduce BT star anyway, I can cancel this BT star, because I'm going to have to take the sum of these guys and subtract BT star. So I'm going to interpret the 9.37 minus BT star. So I'm going to remove this. So I'm going to only interpret these terms, the remaining terms. So let's look at the remaining terms. The remaining terms are these three terms. So notice now, first we had these three terms. Now, one term here also has three more terms in there that I have to interpret, okay? What is the first term? Well, the first term is that if I got the value BT star at time T star, then I have that money in the bank. If I have that money in the bank, then I earn interest on that money at the rate of rho. So I'm losing the interest because I don't have the money in the bank anymore, and the bank is not giving me interest. But the interest, if they were to give it to me, it will be exactly rho BT star times delta. The amount of interest in period delta at the rate of rho on the principal of BT star will be minus rho BT star delta. Good. So the first term is the interest on the resale value that I lost. So there's a minus sign because I lost it, okay? The second term, now notice the second term actually is negative because B sub T is negative. B is decreasing over time. So the derivative of B with respect to time is negative. So this says that I have a lower resale value at T star plus delta. I lost some resale value. So the second term is the decrease in the resale value from T star to T star plus delta. So that's it. What is the third term? The third term is that I'm taking the risk because during this time, T star plus T star delta, with some probability, I may lose the whole value. Remember now, I'm not getting the resale value. I already got the L, right? At each point in time. At each point in time, the machine could fail. So I already figured that out. But I may not get the entire value. So it said the third term is the loss of the entire resale value if the machine fails with the probability, given that the machine was found to be working at T star. Okay. So now we have these terms right hand side minus BT star. If you take the right hand side minus BT star, then I will then let delta go to 0, and I have the marginal profit of keeping the machine from time T star to T star plus delta. And setting it equal to 0 is basically saying that the transfer condition 9.34. Now, remember in 9.34, we have a revenue terms and the cost terms. They're all mixed together. But if we can take all the revenue terms on this side and all the cost terms on this side, then 9.34 becomes marginal profit equal to, no, marginal revenue equal to marginal cost. Okay. Marginal profit is less than 0. Okay. Margin profit is, no, margin profit, keeping the machine at T star delta, setting equal to 0 gives the precise transfer value condition of 9.34, which says that the marginal profit at T star is equal to 0. That's the first order condition of calculus. You take the derivative of the profit and you set it to 0. But economics people like to separate the profit into two terms, revenue and the cost. And they try to say at the optimal solution, the marginal revenue equals marginal cost. That is Newton's first law for economics. Marginal revenue equal to marginal profit. Any question? Notice now, we got all of this with some condition 3.77, which was a condition for T star to be optimal. Then there's some optimal control terms in there. And in the end, we end up with something totally transparent. This condition that is so difficult to put our fans around it apparently becomes very transparent. Now, let me mention to you one more thing. E to minus rho T star is very simple, so we don't have to worry about it. But suppose I put 1 minus F T star back into it. If I put F T star back into it, then this term is multiplied by minus F T star. This is fine, because this one then is exactly this term with 1 minus F T star, okay? But notice what happens. If I put this term back in there, this becomes F dot of T star times delta. So that is exactly what I get. L times F dot times delta, because it's from T star to T star plus delta. So I get exactly that term. So I could have done the following. I could have said, okay, this is what Chen and Schwartz had it. This is how they obtained it by jettisoning those terms because they were constant. And so I want to put one of them back here. When I put one of them back here, then I can change that to F dot of T star. And then I interpret the equation with F dot of T star. So I can then have different looking equation here with F dot in there and another F dot in there. Okay. And I have those two, then I will have those two here, and I will have, again, the same meaning here. But that probability now will be exactly F dot. Because if I put 1 minus F star, that will become the probability. But remember, I call it a probability here. It is not the probability. Probability is with 1 minus f star. So that's why what I said to you is this, that interpreting this is tantamount to setting f(T) star equal to 0. So if you put f(T) star equal to 0, then that is the probability. So it's another subtle thing to catch, is that I'm calling this a probability because I did this. That's why I'm calling it probability. So it's a loose term, but it tells you what I'm doing. But if I put it back, if I put back 1 minus f(T) star, then that would be exactly the probability. And then I don't have to write this sentence, because I will have 1 minus f(T) star multiplied with this whole group here, and I will then have this term with 1 minus f(T) star. I don't have to write this sentence. So I'm thinking whether that would have been better to explain this, but right now I did this. Maybe I will think about it and see if I want to change it. But either way is fine right now. I'm going to take a vote here. If I ask you you five, would it be better as it is? Because now I'm interpreting exactly what Chen and Schwartz had, or I put back 1 minus f(T) star, then interpret it this way and not write this part. If I don't write this part, then maybe there will be extra terms here, 1 minus f(T) star all over the place. These terms will be longer. I will take this in the slide. They will take two lines into the one line, but that's okay. And that would be another way to explain it. It's identical, but it is what it is. What do you think? Anyone has any opinion, or you all think it's okay either way? If you don't say anything, then I'm assuming that you are saying it's okay either way. No more questions? It is very clear what is going on. Any improvement in the language here that will make it more clear for any one of you? Every book has a goal of being perfect, but it's never perfect. Only as time goes to infinity becomes perfect, but it's never perfect. Oh, by the way, one more thing. And Kushali, I already sent you the email. This term, let me go here. This term has to be f star of t star. Notice if you look at the equation 3.77, and if you look at equation 3.77, and later on in some of the boxes in chapter 3 and chapter 4, we have a t star optimal equation. In that equation, we have x star of t star. Now, this f is really x. It's a state. And so if I were to follow that 3.77, I would have this to be f star. Okay. And I sent Kushali already an email that should be changed to f star, that should be changed to f star, that should be changed to f star. So on slide 33, f should be f star in 3 places. And that would also be changed in the book, because in the book, I also have it f and not f star. Okay. So that's something that, again, you see, it's not going to create problem for anybody, but just to be correct, I should have it f star. Okay. I am not having I'm not having, let me try this now. Okay. Yeah, you have to do that to get back the. Okay. If there are more questions, we move on. The next thing to do is, so this is the optimal sale date policy. The next one is optimal maintenance policy. And this policy is basically saying that as far as the optimal maintenance is concerned, I can just fix T because it is, I can interpret it for every fixed T. Then it gets interpreted also for T star. So this is for more general setting. I just fix T. If I fix T and take the derivative of H with respect to U, I get this equal to 0. Now, in order to interpret this equal to 0, you can see that this is 3 different terms. One term, second term, third term. When you have a product that equals to 0, it can be 0 by any of the term becoming 0. So you need to you need to think about that. Okay, it is important that you think about it and not just go straight to this slide here, because that slide is not complete unless you tell you, because this doesn't have to be 0 if these guys become 0, right? Okay, so in the trivial cases in which the natural freight HT is 0, which means machine never breaks down, okay, or when F is 1, which is when this becomes, the second term becomes 0 when F equal to 1. So the first one, when H is 0, it means machine never breaks down. That's not our model. We don't assume H to be 0. The second one is machine fails with certainty by time T. It's F equal to 1. That's not our model either, because we don't assume any particular time by which machine fails. Okay? So if that's true, then we know the optimal solution U star T equal to 0. Because why would you put any maintenance if you know machine is going to fail anyway at that time? Then machine is producing R until that time and fails at that time. Control has nothing to do with it. You don't need any control. So by saying that, we can do the following. We can therefore safely assume that H is bigger than 0 and F is strictly less than 1. And under these conditions, this Hamiltonian maximizing condition gives you that equal to 0. That equal to 0. So this is a condition that will give us a U star. And that would be an interior solution, because if this gives me U star, which is between 0 and 1, strictly between 0 and 1, then I can use that. So here we go. If this is equal to 0, gives me strictly between 0 and 1, then that gives me U star T. But if it's bigger than 0 for every T, then I set U star T equal to 0. If it's smaller than 0 for each T, then I set U star T equal to 1. This is understandable. This is every maximization problem with a boundary condition requires that interior solution is equal to 0 and the boundary conditions are less than 0 and bigger than 0. Okay, so those are the conditions here. So that characterizes U star T. Now, because we know lambda T is given by this, then I can substitute that there and I can interpret this at capital T. So at capital T, what happens is this. If this is, then I give a U star T, which is between 0 and 1. If it's this way, then it is U star T equal to 0. If it's this way, then U star T equal to 1. So I can actually find these conditions a priori, because I know BT, I know L, I know this. So I can actually find out using 9.40, what is U star T? What is the optimal U star T? Okay. One thing that also Chen and Schwartz does, and this is, I think, left as an exercise for you. It's exercise 9.10. It says, what, remember in Thompson's model, we also had a change of U star T over time. Okay. In the first model in Thompson, we said that the control can go 1 and then go to 0. So it can stay 1, it's a bang-bang solution, and it then goes to 0, okay? And in the Thompson's model, there was no singular control. Then after Thompson model, I have an extension, which is, I think, my model somewhere, which I changed the Thompson model to a nonlinear model. And I show that the control is 1, then it goes down to 0 in some fashion, and then it becomes 0. So that it goes like this, goes like this, goes like this. And that, I also mentioned that it can go like this, it can go like this, depending on the function there, but it's decreasing for sure. So that was a small extension of Thompson model, which is not a serious extension or serious modification of Thompson model as this one is. As Chen and Schwartz is a way more serious modification of Thompson's model. Not just modification, it is alternative. It's a different model, let's put it this way. So Chen and Schwartz also show that you can find switching time T1 and T2 such that optimal control is 1 between 0 and T1, and then it's U0T between T1 and T2. U0T is given by this guy, and then it is 0 for T2T. So it is actually going down. It is if you think about it, it's going like this. It's like this. This is your T1, this is your T2. So it goes like this, goes like this, goes like this. This was in the extension of Thompson that I did, but Chen and Schwartz is saying that they get a similar solution in their problem as well. Okay. Notice when you have this picture here, we are allowing T1 to be 0. If T1 is 0, then this portion disappears and controls start decreasing right away. If T2 is capital T, then this portion disappears, and we have this going all the way like this, like this. So all of those are allowed in this setting. Okay, nothing this, all of this, they're all allowed. So the same thing in Chen and Schwartz case. You are asked in exercise 9.10 that this U0T that comes because of this condition, that this condition allows you to show that U star dot is less than 0. Okay, so you have to take the derivative of this condition one more time with respect to time, and then conclude that this is less than 0. That is left as an exercise. Okay. There's another exercise, which is that this model is also sufficient optimality, and the sufficiency condition applies the maximum principle. So that is exercise 9.11. So we are done with Chen and Schwartz model, and I'm going to now switch on to the next model, which is my model, with another professor at Carnegie Mellon at the time. Are there any questions? You guys are extremely quiet, okay? That's why I don't like these virtual classes. I think it's better to have in-person classes where you can have eye contact and then ask people the questions. Maybe you like this way. Nobody ask you any question. Okay, let's continue. So while reading Thompson's model when I was a PhD student at Carnegie Mellon and looking at Chen and Schwartz as well, I thought that that problem needs to be extended. first of all, they call it maintenance replacement, but it's really not a replacement problem. It is actually a sale date problem. And Thompson had it right. Probably some referee told him to replace it by replacement by sale date. I don't know. Paper was published before my time. Um, so I decided that I need to figure out how to extend this problem. Now, there is a whole lot of literature on machine replacement problem, which is not control theory related. But that literature has no maintenance because it's a maintenance over time, which is the dynamics in a control problem. If you don't have the maintenance, then the problem is simply replacement of the machine. Okay, you can have a maintenance which is not controlled. That's okay, but it is just simply a replacement of machine. And I had a PhD student who is now a professor at Purdue, who was a PhD student at Carnegie Mellon, but I left. I actually was teaching at Carnegie Mellon in 1978. I went back to teach there as a visiting professor, and there was a PhD student there who worked with me, and I looked at the problem of machine replacement more seriously at the time. But anyway, this is the problem that I was working at that time. Let me see now. Anyway, it doesn't really matter. So I was looking at this problem, and I kind of had half, maybe more than half solved the problem, but I still had a little difficulty of how to go from one place to another. I'll tell you that later. So let's go to the model first. So that replacement literature assumes number of things. One of the things it assumes is that every machine to be replaced at the same time. That means I decide a time, let's say 2 years, and I then must replace the machine every 2 years, and I optimize over that 2 year. It could be 2 year, could be 5 year, could be whatever, but I find the optimal replacement time. But it has to be constant. This is called identical kind of machine lives. But I also didn't like that because machine technology is changing. And if that's happening, then there's no reason for us to have I remember the computers. My IBM PC, the first one I bought, which was the original IBM PC, it stayed for some time. Nowadays, the computers are being replaced much more often than it used to be before, in some sense. And so technology, how the technology changes has impact on what is the optimal life of the machine. And I've written several papers on that in this field. So let's look at this problem. It makes sense for this problem to be looked into finite horizon setting because it's kind of difficult to have an infinite horizon machine, infinite horizon, and then have T1, T2, T all the way to Tn, with n going to infinity. It's an impossible problem to solve. Okay, and it is also useless because nobody can forecast technology all the way to infinity. And so it is really not a very interesting problem to solve. I think the interesting problem is a finite horizon problem with non-identical lives of the machine, depending on what happens during the life of the machines. So I said, okay, we take a t-period problem, and we take T1, T2, TL minus 1, TL is the time at which the machine will be replaced. Notice L will be less than T, but I don't know how many. I may replace the machine, first machine 1 month, second machine after. No, first machine may be, let's say T is 10 years. I can replace the first machine after 2 years, the second machine after 1.5 years, third maybe after just 1 year. So I don't know how many machine I would be needing in that 10-year period. That has to be found out by optimal solution. So what I'm interested in finding a optimal number of replacements, and for each machine, the optimal maintenance. That's my problem. That's what I'm working on right now, okay? So I said, okay, the first thing I can do is find any 2 consecutive time, fix them, and find the optimal maintenance of that machine. That is my sub-problem. And once I have that, I need to figure out how to do this entire problem. Okay, so this is the game right now here. So 2 approaches to the problem have been developed in literature. One is T equal to infinity and identical machines. You see the identical machines? But this is not very satisfactory because identical machine is not so important as having non-identical machines. And if you have to have a finite time for that, then so be it. Okay, this is less important than relaxing this assumption is not so. No, changing this assumption is not so much of a problem. Relaxing this assumption is important. So I'm now giving you a paper by Sethi and Morton that was published in 1972. I finished my PhD in 71, but I got graduated in 72. The certificate came to me in 72. Okay, so the published version of the paper was not part of my thesis. Carnegie Mellon was interesting in the sense that my thesis, which had 10 papers, and I think a couple of them were already published, so I actually didn't type them. I actually stapled the published paper into the thesis as they were. And they say it was okay. So that was nice. That was not part of it. Well, that did not get published before 71. Okay, so let's go. Consider buying a machine at the beginning of period S and salvaging at the beginning of period T, which is bigger than S. So I take 2 arbitrary time S and T, and I find out this problem because it's a control problem. It's the same control problem as a Thompson control problem. Okay, so I can solve that problem according to Thompson in some way, although I change a little bit, but that change is not serious. I just do it anyway. But I do it discrete time now. Okay, because the whole problem is discrete time. S and T are discrete. So letting Thompson, small s is the vintage of the machine. I buy the machine at time S. Okay, so that's the vintage of the machine. And the vintage is synonymous with technology of the machine because I buy the machine of the latest technology. I don't buy a 3-year-old car that is sitting in a garage somewhere. No, not unused. I buy the car of the current year. Okay, that's machine. So XSK is the resale value of the machine at the beginning of period K up to T. So this is like a Thompson's function B. This is like a Thompson's function, no, or the Chen and Schwartz B. Okay, it is the value of the machine at time T when we sell it. So that is some feature of something that is given to me. PSK is the production quantity in dollar of a machine that was bought at S and sold at T. So in between, it produces. I also add something called necessary expense, which means something that I have no control over it. It is like what the companies tell you this machine requires. And this is like in the car, and it comes with a manual, and every 6 months or so, you go to the dealer, and then they fix and take care of it. And for 3-4 years under the warranty, you keep doing that, and that is your necessary expense. That's not preventive maintenance. And to simplify, I can do this. I can define R sub Sk to be the difference of these two. Notice the periods here. Again, for you to understand discrete time, it's better to have a picture of where the period begins and where it ends, kind of thing. Notice now I did here, for example, my period are labeled as 0, 1, 2, up to t minus 1. So these are the periods labeled, and then S and T will be labeled in those periods. UK is the rate of preventive maintenance during period K. CS is the cost of purchasing a machine at the beginning of period S. So S is like this. This is the beginning, this is the end of S. Rho is the discrete discount rate, periodic discount rate. I assume that U sub K, which is the control, the upper bound of the control depends not only on K, which is the period I'm in, but also depends on the type of machine that I have, which is given by S. So I have a bound on the control, which is very similar to Thompson and Chen and Schwartz. And now I have my machines don't fail. By the way, I will tell you that after I wrote this paper, many years later, professors at Columbia wrote this kind of paper for Chen and Schwartz kind of model where machine could fail. Because machine could fail, then what happens is when you replace in this interval, S and T, machine can fail between these intervals. So then what happens is if you have a T period and you have certain point at which the machine will be replaced, but actually my machine may be replaced more often than those periods because machine may fail even before that, and then you have to replace it. So they make an assumption that when it fails, you have to replace it. So that is more complicated model, and that was published in Operations Research by these people. And one of them was the president of Bilkent University in Turkey. And he was a friend of mine, so I visited him at Bilkent one time, and I stayed there for maybe 1 or 2 months, I don't remember. And we wrote another paper that extended that paper. And then one of my former students, Annabelle Fang, who's now a professor at Purdue, I got her involved to do some numerical calculations on that, and we published that paper recently, or not recently, but a few years ago, in a book somewhere. Okay, so that's the history of this kind of work. So now we have to do the objective function for this machine. I will call it JST, a machine that was bought at S and sold at T, from S to T minus 1. I have revenue, which is discounted this way. I have a cost of preventive maintenance. Remember, this revenue has P minus E. So preventive maintenance. And of course, now I also have to subtract the machine purchase price. Because if I only one machine, the purchase price is fixed and sunk. But if the machine price is changing over time, then I can find out when to buy the machine. It has an implication on when to buy the machine and when to sell the machine, right? So I need to factor that in anymore because I have to factor in now. So I have to subtract the cost of purchase from this, and I have to add the sale value at time t and discount that with minus t. So this is discount minus s, this is discount minus t, this is for each k, and this is for each k. So this is my objective function. So this model is going and trying to get a little bit more practical aspect in there. Now, this is the teaching part of it. I decided that since we did something in continuous time part of the book that asks you to change a Boltzmann form problem into a Meyer form problem in continuous time, which we did, I decided that I will solve this problem in Meyer form. It's just a taste, a matter of taste. And I did that actually because I wanted to bring in that transformation into the book in a discrete time setting, which was not done before, and it wasn't done in chapter 8, so I'm doing it now. By the way, this chapter 9, this model of chapter 9 is one of the, well, not one of the reasons, but it is in a discrete time, and I need a chapter 8 to tell you how to apply a discrete time maximum principle. So that's why this exists in chapter 9. So I'm now going to change the problem into Meyer form. So the first problem is without the Meyer form. So I'm sorry, I'm going faster than I got the objective function. I also have to give you the state equation. Assume that time s, the only machine available are those that are up to date with respect to technology. That means the newest machine at that time available. So I can substitute the technology prevailing at time s, which is the best technology at time s that I'm going to buy, and subscript this function by s to reflect the effect of the machine's technology on its state at a later time k. Let psi s u k k and phi s u k k be such concave functions so that we can write the following state equation. I'm now telling you that if I use UK maintenance in period K, which is this right now, and I have a machine of technology S, then my revenue will be enhanced or not enhanced, or the change rather. This is the way that R will change. This is given function now for every UK. And RSS is given because RSS is the revenue of a machine that bought at S in S period. I also tell you how the machine, now you notice what is going on. This is the resale value. So I also tell you that the resale value of the machine will change according to this function. So a machine bought in period S and using UK as a maintenance amount in period K, then in that period, the change of resale value will be given by this function. That's also given to me. I also tell you that the change in the XSS is the resale value of the machine that I bought in period S, its resale value in period S. Well, I bought it machine as CS, and there is something called an out of shop depreciation. If you buy a car today for, let's say, $30,000, like Monday morning, and 1 hour later you want to sell that car, you will not get $25,000 for it. You will get maybe 10% less. And that 10% is this delta 0.10, 1.10. So 1 minus delta is the value of the machine, the sale value of the machine that you will get of a new machine immediately after you buy it. So that is your initial condition. Okay, that's also given to us because CS is a function that's given to us. CS is also a forecast of technology in the sense it is a forecast of the price of the machine from here all the way to capital T. So I have the dynamics. So given these two equations, given that objective function, and given that constraint, I have a control problem. A discrete time control problem has been now written. The next thing we're going to do is to solve it. When we solve it, I'm going to try to do a Meyer form. So here's a Meyer form. Take the, instead of integral from S to T, I'm going to take integral or sum from S to K minus 1 of this R guys, these R guys, these R guys. You notice this I here, I goes from S to K minus 1, I take the sum. I call this to be ASK. This is a new state variable, okay? This is Meyer form state variable. I also take this guy, BSK, is the sum of the controls discounted from S to K minus 1, call this. If I do these two, then I can change the objective function, which is these guys. I can remove the sigma. And there's no sigma here. So I can change the objective function to be like this. So these are my state variables. This is my initial cost. This is my salvage value, which is the Meyer form allows me. This is the terminal value. This is the terminal value. This is the terminal value. So these three are the salvage value, kind of. That's Meyer form. And this one is the initial thing, which is for this particular problem is given. And so you can remove it if you want, but we want to keep it for accounting purposes because we are not done with it. This is just a sub-problem between S and T for any given S and T. So I need to keep, even though it's constant for the optimal control problem, I need to put that into it as an accounting device so that I know the total profit associated with this machine, including allowing for the cost of purchase. When you do this Meyer form, then the dynamics of this is simply this term, and initial value is 0, and the dynamics of this one, delta BSK, is this term, and BSS equal to 0. So now this is the Meyer form, the optimal control problem. Objective function, dynamics, but we also have the dynamic. These are the two equations, but we cannot ignore though we also have these dynamics. So we have 4 equations. So we have 4 state equations. This one, this one, this one, and this one. So what we have done is increase the state equation, but simplified the objective function. Either way is fine. I mean, this is just my way of showing Meyer form along with the optimal control, discrete time, and then the model itself. Okay, and of course the optimal control problem also required this. So 9.43 along with 9.43 along with 4.5 and 4.6 along with these and this objective function, I have an optimal control problem. Okay, that's 9.43. So we have all of that. This should not be called constraints. Kushali, can you make a note of this? It's not there. Okay.
Yes, Professor. I'll make a note of that.
Yeah, just make a note of that because I already sent you the other thing. Oh, the thing stopped.
I think the screen closed. Let me open it up again. Oh, and did you mean to take a break? We didn't take a break at all today.
We can take a break right now. Why don't you do that?
Okay, well, let's do that.